The first way we're going to solve our problem is using the stepping stone. We're going to use the stepping stone, kind of like stepping on stones across a brook. The key to this is the unoccupied cells. Just to highlight the unoccupied cells, I have them circled in red. I'm first going to try and step 1 unit in from Winooski 2A to check to see if that will lower my shipping costs. You notice I've set up a box. Look at the pluses and minuses, because if I add 1 unit to Winooski, that would bring me up to 83 units of supply, and I only have 82 available, so I have to take 1 away from B. Same thing with if I look at the demand for A. If I add 1 to Winooski, I have to take 1 away from Concord, so I maintain the demand of 72. So in that way, I step around the box. Now, if I took 1 unit from each, this is what the transportation costs would look like. I added $16 to transportation because of Winooski. I took 24 away because of Winooski to B. I've added from Concord to B, and I've taken away from Concord back to Acorn. So that gets me a net result of $0. So I'm trying the unoccupied cell of from Concord to Comfy, or to C. I'm going to move 1 unit in. Again, I have to adjust to make up for my supply and demand. So you can see again the box. So I have the pluses and minuses, and I move around the blocks. Again, I take the transportation cost. To move from Concord to Comfy, I'd have to add $24 of transportation, take away 6, add 24, take away 16. So all in all, it would add a bunch of money trying to move. Next, we check the cell from Rutland to Big Budget or B. You notice we've done more of a rectangle than a square here. 3 out of the 4 sides have to be occupied cells. Again, same idea. If we move 1 unit into Rutland to Big Budget, we have to take 1 away to satisfy our supply and demand, so we have the box going there. And this is what it would look like with my transportation costs. I add $8 of transportation costs, take away 16, add 8, take away 4. So that gives me a negative $4 of transportation. So finally, we get to our final unoccupied cell, which is from Rutland to Comfy, or C. This one's a little bit more complicated, because you notice I have to do what I call a double box. So I go, if you can follow the arrows around, it's almost like I combine 2 boxes, because I only can have 1 unoccupied cell. All right, so I went add 1 to C, take 1 away from Winooski and C, add 1 to Winooski and B, take 1 away from Concord and B, add 1 to Concord and A, take 1 away from Rutland and A, and back to the beginning. Okay, here are our 4 blank cells and their value. Again, we added all the transportation cost as we stepped around the boxes. You notice Rutland to Big Budget is negative 4. We know that the transportation problem is a minimum cost, and these sums represent our net evaluation row, or think of them as the net evaluation row. And we know that for a minimum cost problem to have optimal, every number in our net evaluation row has to be greater than or equal to 0. We can see Rutland to Big Budget is a negative 4. So we know that we're not optimal, and that also tells us that that is the entering variable, that we're moving units into Rutland, into Big Budget, from Rutland into Big Budget. So it looks like this on our chart. Now, I had my choice. If I have 2 negatives. I had Rutland to Acorn, which was 56, or Concord to Big Budget was 61. The leaving variable is the smallest negative. So 56 is less, in the negative cell, is less than 61. So I subtract 56 from 56, I get 0. I bring that 56 over to B. You notice that keeps the integrity of my supply. Rutland only has 56 units, so now I've just transferred them from A to B. All right, but now I've added 56 units to big budget as demand. So I have to take away 56 units from big budget to Concord down the bottom. So I went from 61 units delivering there to 5. Same thing, I have to keep the integrity of the supply for Concord. So I can't just add 56, I can't just take away 56 units, so I have to add those to Concord. So this represents my improved solution. Okay, I just cleaned it up a little bit, but this is what our improved solution looks like. You notice we can calculate the total cost, and it's gone down from 2,889 down to 2,744, so we have saved cost. Now what we'd have to do for step 6 is go back and repeat, check for optimal, and move on.